Hello there, stats students. Today we are starting section 12.2, which is our final section of this chapter and the textbook. We're going to be looking at transforming to achieve linearity. So here's what we're going to look at. So if you think back to chapter 3, we looked at analyzing relationships between two quantitative variables, and we looked at scatter plots that had linear patterns. When we describe the shape of those plots, we either said they were linear or they were not linear. So what we're going to finally do here is we're going to look at how to analyze data that actually show a curved or nonlinear relationship. And the way we're going to do that is by transforming the data. So once the data have been transformed, then you can then use the least squares regression stuff we learned in 12.1. All right, and we check the same conditions. So basically, we're going to focus on how you transform the data to achieve linearity. We're going to be looking at using math functions like logarithms and square roots and exponents to transform the data. And we're going to look at how using those can help us make linear patterns out of nonlinear patterns. So one example, and this is from a website, Gapminder. This is a graph of the income per person in a country compared to the life expectancy in that country. And so you can see each dot represents a different country, and then the size of the dot represents how big that country is. And I think the color is based on what continent or region in the world it's in. But you can see here that the general trend is a positive trend. As one goes up, the other one goes up. So that means like the wealthier countries tend to have greater life expectancies. But you can see this clearly curved shape. Now you'll notice this is the same data, but now it looks linear because if you look at this axis down here, it doesn't count by the same thing. This counted by 20,000 every tick mark. Now they double every tick mark. That's because this is now a logarithmic scale on the x-axis, and now the data looks linear. This was back in 2015. Here's the data for the more recent years of 2019, and you can see still a slightly curved relationship. It looks a little different because the maximum value changed quite a bit, which makes it look maybe not as curved. It is just as curved, though. It's just we're not don't have as big of a maximum down here. And then if you change it to a logarithmic scale, you do get this more linear shape. So what we're going to look at, though, is we're going to look at first using powers and roots. So not logarithms yet. That'll come in our next lesson, but we're going to look at powers and roots today. So let's say you visit a pizza place and you order a pizza by its diameter. You either get a 10-inch, a 12-inch, or a 14. However, the amount of pizza you get to eat doesn't depend on the diameter, it depends on the area. So the area of a circle, pi times the square of its radius. So if the diameter is x, you need to do half of the diameter, square it, that's the radius, square it, multiply it by pi. So if you then square x over 2, you get x squared over 4, and then you can combine those into a single fraction or multiply them together, and that's another way to write that as pi over 4 times x squared. Now this equation is called a power model of this form, y equals a times x to the power of p, where a is pi over 4 and p, the power, is 2. So although the power model of this form describes a relationship that is not linear, okay, there is a linear relationship between x to the power of p and y. So basically, if you transform the values of the explanatory variable x by raising them to the power of p and then graph x to the p comma y, then your scatter plot actually has a linear form. Other examples of real-world situations that use power models, the distance an object is dropped from a height compared to its time has this form, which you can see as a power model, where your power is 2. Another example would be the time it takes for a pendulum to complete one back and forth swing, related to the pendulum's length. If you remember in physics, that has like a square root in it, which we can just call an exponent of 1/2, and that's still called a power model. or the intensity of a light bulb related to the distance from the bulb. This is a divided by distance squared, which you could just write as distance to the power of -2. So you can see that our power here could be whole numbers, positive whole numbers, fractions, or it could even be negative numbers. These are all example of power models. All right, let's take a look at an example here. Imagine you've been put in charge of organizing a fishing tournament, and there are prizes for the heaviest Atlanta Ocean rockfish that is caught. Now, you know many of the fish caught during this tournament are going to be measured and released, but using scales on for a fish that is flopping around in a moving boat doesn't yield very accurate results. However, it is much easier to actually measure the length of the fish while on the boat. So you need a way to convert the length to the weight. So here's data collected for several rockfish of their lengths and weights. Now, if you plot the lengths compared to the weights, you will notice there's a curved relationship, clearly. So here's what we're going to do. Length is a one-dimensional measurement, and weight, much like volume, is a three-dimensional measurement. So we're going to use a power model that is weight equals a times length cube. All right. Now, if we transform that, basically what we're going to do is we're going to cube all the lengths. So I cube all these numbers. And now on the y-axis, I'm going to have weight, but on the x-axis, I'm going to, instead of putting these lengths, I'm going to put the cube of the lengths. Now, you'll notice when I do that, I get a graph that is quite linear. Alternatively, okay, I could transform the data to achieve linearity by, instead of cubing the length, I could do the cubed root of the weights. So if I take all these weights and do their cubed roots and make that my y-axis and leave the normal length as the x-axis, I get this graph. Once again, you can see that it is now a straight pattern. Okay, and then for this data right down here, I could then fit a least squares regression line to this transformed data. Now let's take a look at these two examples though at the same time, because there's kind of two different options for this data. Now, if you do the length cubed compared to weight, you get this regression here. You get this, y-intercept and slope. You can see the r squared's very high here for the transform data. And then if you do instead length compared to the cubed root of weight, you can see this y-intercept and slope and this r squared value. So again, very strong relationships no matter which way you do it. Here then are the residual plots. Now you might say, well, that's not quite random, it looks a little off, and especially maybe this one, but for our purposes it is good enough, and you can see that they are actually very small residuals comparatively, so it's not a huge concern that there's a slight shape to that. But basically, using these output tables, what's the equation of the least squares regression line? So basically here's the y-intercept and the slope. However, y-intercept plus the slope times, instead of x, you can see that the x value is actually length cubed. So I put length cubed right here. And the y value is weight, so I put weight hat, or predicted weight is what that means. And then for this one, that's the y-intercept and that's the slope. So the y-intercept plus the slope times, you can see the x value here is just length, but then the y value is the cubed root of weight. So it's cubed root of weight hat, or predicted cubed root of weight. All right. Then suppose that a contestant catches a fish that is 36 centimeters long. So let's use the two models to predict the fish's weight. All you have to do is plug a 36 in here for length and plug a 36 in here for length. And let's see what we get. So I plug in a 36 in there, I have to cube it, multiply, and add, and I get 688.9 grams. In transformation 2, I plug in a 36, I multiply it, I add that, I get 8.856. Now those aren't even close. Well, that's because this transformation is what the cubed root of weight will be, so I still need to cube this number to get my final prediction for weight. So I cube that and I get 694.6. You'll notice they aren't the same value, but they are, pretty close. Now, interpret the value of S. So this is S right here for transformation 1, this is S for transformation 2. S is the standard deviation of the residuals. So the way you interpret that for transformation 1, The standard deviation of the residuals is 18.841 grams. Predictions of fish weight using this model will be off by an average of about 19 grams. That's how you can interpret S. Now for transformation 2, it's just slightly different. So for transformation 2, S is 0.12. Okay, that is predictions for, notice the difference here, predictions for the cubed root of fish weight will be off by an average of about 0.12. It doesn't mean that this one is way better than this one, because they're actually predicting the different things. This one is predicting weight, this one is predicting cubed root of weight. So when you interpret S in this one, make sure you're clear that this number is what predictions for the cubed root of a fish's weight will be off by on average. So when experience or theory suggests that the relationship between two variables will have a power model, that means we have two strategies for transforming. So we can raise values of the explanatory or x variable to the power of p, and then plot x to the p against y and see if it looks linear. The other option is you can take the pth root of the response variables y, and you can plot all the x values with the pth root of y. So those are basically the two approaches you can take to achieve linearity when a power model is appropriate. Now, there are some times, though, like some of these situations, you might know, oh yeah, that's definitely a power model. If you see something like one of these, or something that relates area to length, or something like this that relates volume to length, then you would know a power model is appropriate. But there might be a case where you don't know what to choose. Now, you could guess. You could just try squaring it and see if it looks linear, or try cubing it, or try a fourth power, or try a 1/2 power, or, you could try things. There are even some computer programs that come with built-in things where you can, drag sliders around to adjust it and see what happens to the shape. However, instead, what we're going to do, and we'll learn this in our next lesson, is there's a much more efficient method that if you're not sure what number to use, and that would involve using logarithms. Woo! Everyone's favorite, yes. Now, this more general method works when the data follow an unknown power model, or there are actually a few other types of models that aren't power models that logarithms can help with as well. So you can look forward to working with logarithms in our next lesson. So that's it for today. Of course, let me know if you have any questions.